This is the amount of time it takes to go path 1. Now what about path 2? That's a little bit more complicated. Path 2. So I just blew up path 2 a little bit here just to show the first the light goes from the beam splitter to the mirror. Whoops, this is the beam splitter. From the beam splitter to the mirror. But because the ether is blowing the light to the right, and the path of the light ends up being straight up. That's the resultant path, right? That means that in order for it to follow that path, the light that's traveling at C the light must be doing this, right? This is C. The light is traveling in that direction, being pushed backwards by V, so that the net result is traveling straight from the beam splitter to the mirror, because the ether is blowing through. So that must be true in order for the light to go from the beam splitter to the mirror along that path. So the velocity of the light here, we can call that U is the velocity of the light. It's going to be, what is it? Well, you should be able to do that. It's geometry of the right triangle. It's square root of c squared minus v squared. Okay. Then the light that's coming back, whoops, let's draw that. The light that's coming back, going to have the same kind of thing, right? So the light that's coming back must have been blown to the right by V, and so C must be, oh, wait a second, C plus V. Oh, right, sorry, sum of two vectors, the sum must go from the head to the tail, so I drew that incorrectly. Sorry, the sum must go from the tail to the head, oh gosh. Yeah, from the tail to the head of the sum of two vectors, so I drew that incorrectly. So V plus C, if this is C, when it's on its way back, I think I got it right this time, in order to follow the straight down path back, it actually must be C, in the picture that I've shown on the bottom here, down and to the left, and V pushing it back to the right, so that the resultant vector is this one, and the velocity there is also the square root of c squared minus v squared. So it's easy enough to show that the time for path 2, T2, is the time up, and let's just say path 2 is the same length as path 1, it doesn't actually really matter here, L over the square root of c squared minus v squared. That's on the way up, and on the way back, it's L over the square root of c squared minus v squared. So that's right, the up trip and the down trip. So that's the total amount of time that it takes to traverse path 2. So we're interested in what the difference is between those two paths now. And that's still not going to give us the answer, but we are interested in the difference, so we're interested in delta t. Delta t equals t2 minus t1, the difference in path lengths, or the difference in path times, which could be made equivalent to path length difference. And we can write that out as 2L over the square root of c squared minus v squared minus L over c plus v plus L over c minus v. Now, I might have this backwards. That might be a negative time. It doesn't matter, but I'd like to keep that positive, so it might be the other way around. It doesn't matter. But that's not what gives us the interference pattern. What gives us the interference pattern are two beams meeting, and they're spread out over the screen, and so they interfere at different places. What gives us the interference pattern is changing something. So even though I have a delta here, we haven't changed anything. This just tells us the difference in time. And maybe I should actually call this something else. Now I won't even bother. Okay, but we haven't changed anything. So now what we're looking for, so we've gotten an interference pattern just because we have light in the interferometer. Now what we're looking for is to change something and see how this interference pattern changes. And what we're going to change is we're going to take that interferometer and we're going to rotate it 90 degrees. So we're going to rotate the whole thing 90 degrees. So now the two legs have changed so that T1 is now what T2 was, and T2 is what T1 was. Okay, so let's just not go too fast here. They put it on a rotating table, so they were able to rotate it without knocking over the mirrors. and they rotated the whole thing 90 degrees. Okay, so in place, they rotated the whole thing 90 degrees. And so what happens is when you rotate the whole apparatus, what was T1 is now T2, and what was T2 is now T1. And that, just think about it, algebraically, whoops, this doesn't look right, okay. Algebraically, that's the same as shifting one leg, one path, relative to the other by 2 delta t. So the change in t, right? So now, therefore, right, delta t new is equal to t2 new minus t1 new, and delta t new minus delta t old, or the change in delta t, is 2 delta t. So the act of rotating the whole thing 90 degrees tells us that the interference pattern should shift as if we shifted one of the legs by 2 delta t relative to the other. As if we slowed down one leg by 2 delta t relative to the other. That's what this tells us. So now I've just rewritten it. If we slow one leg down by 2 delta t relative to the other, that we get by shifting the whole apparatus by 90 degrees, then it falls behind by a distance. So that what we have is time so far, but it falls behind by a distance of 2 c delta t. Distance equals rate times time. Now you might say c, why not c plus v? Well, that's too small a difference to matter. It's too small a difference to matter. You will see that the approximation of putting a c in here, I think you'll see, should be fine. So it will fall behind by this distance. And if that distance that it falls behind by is half a wavelength, then you're going to shift the whole interference pattern by half a wavelength. If it's a quarter of a wavelength, you're going to shift the whole interference pattern by a quarter of a dot, the spacing between two dots. A tenth of a wavelength, it's a tenth of the spacing between the two dots, etc. So that's the concept of the interferometer, and that's the concept of the Michelson-Morley experiment. In the Michelson-Morley experiment, what they were able to do is to do this experiment and show that to the accuracy of their measurements, that delta t, that they saw no shift in the interference pattern. So they found that delta d equals 0, which would mean that v is equal to 0. Okay, so in actuality, I can't remember exactly what it was, but if they said that their accuracy, they could probably measure 1/100th of a wavelength shift, then they could put a lower bound on v. So that's really important, right? There is no such thing as a 0 result in any experiment. So what they really could do is they could say, well, delta d can't be any bigger than a certain amount, so v can't be any bigger than a certain amount. So they were able to put a lower bound on v. And that lower bound made them conclude that v was pretty close to 0. And it doesn't really make sense for v to be really close to 0 because remember v in this case is the speed of the ether. Shouldn't the ether be carried by the sun more likely than the earth? And we're moving at 18,000, or I can't remember what it is, but I think it's something like, we're moving very fast, 100,000 miles an hour relative to the sun, or I don't know. We're moving very fast relative to the sun. Look it up. You can figure that out. And what they were able to do was put a lower bound of a couple hundred meters per second. So it didn't make sense that there would exist an ether. So the ether does not exist because they put a lower bound on v, and that lower bound was really too low to say that an ether wind existed. Well, is that really true? No, they were just able to say, we're pretty sure that ether doesn't exist, and it took further experiments for many years further to say for sure that the ether doesn't exist. But we now know that the ether doesn't exist, hence Einstein can do special relativity with his postulate 2. Right? So no ether, therefore C does not have a preferred reference frame. C is constant or the same in all inertial reference frames. If you're moving relative to light source, the light is still moving at c relative to you. Bizarre, bizarre, bizarre. That comes from both Maxwell's equations and the confirmation that there is no ether. Now I'm going to come back to this result, because you look at this result and you say, you did all that work for this equation that we're not going to use, right? Actually, we are going to use this equation. I want to look closer at this equation and do some math, some more math with this equation, and show the accuracy of their experiment. That's next time.